So, dear students, welcome back to this analog electronics circuit. Myself Pradeep Mandal from IIT Kharagpur. I am associated with E and EC department of the institute. So, we are going through the second module and so it is continuation of that. Namely, we are going through analysis of nonlinear, simple nonlinear circuit containing BJT and MOSFET. In the previous submodule, we have seen that the circuit containing BJT, how to analyze it, and today we will be going to similar kind of analysis, but containing MOSFET, and we will also see what will be the difference. So, so let us see what are the things we are planning to cover today. So, first we will cover the basic circuit configuration. As I said that it will contain only one transistor, and then through two examples we will see how we can find the circuit solution, namely the circuit current and voltage. And then further we will be going through the example, and in fact, incidentally that example, it is common source amplifier, where the source is common for input and output, and we will be seeing that what will be the output for varying inputs, and then from that we will be giving a thought towards what may be the output variation whenever we are changing the input. So, in other words, input to output transfer characteristic of the circuit. And then if we change the input in a regular pattern or maybe through some signal, then we can see at the output what kind of signal, the associated signal we can get at the output. Namely, if we give a signal at the input of the common source configuration, what kind of signal we are expecting at the output, namely we are expecting amplified version of the signal. And then we do have a plan to cover some numerical examples. If time permits, we will go a little detail of that. Otherwise, probably we can give some hint, and then you can work out those numerical problems. So, according to our overall plan of this course, in this schedule, let us see where we are. Yeah, so in this module, namely week 2 modules, we are going through this nonlinear circuit containing only one transistor, and as I said that previous day we have covered circuit containing one BJT, and today we will be going through similar kind of circuit containing MOSFET, one MOSFET. And the overall plan, as I said that to find the input to output transfer function, and then also how the circuit can amplify a signal. So, in other words, how this circuit, simple circuit containing one transistor, can amplify signal. So, this is what the plan, and as I said that compared to previous days, it will be the transistor instead of BJT will be going through MOSFET, and whenever it is appropriate, we may also discuss about the difference between the circuit containing BJT versus circuit containing MOSFET. So, let us see the basic circuit configuration. So, here we do have the example circuit, we called example circuit 1, and you see here we do have supply voltage, main DC supply voltage VDD, which is giving supply to the drain of the transistor through resistor R, normally referred as load, and at the gate we are applying VG, and we are assuming that the device, it is in saturation region which is equivalent to active region of operation of BJT. Namely, in the channel, if you see the drain end, the channel pinch off, it is happening. And if that condition is satisfied, in other words, if VDS is more than VGS minus VTH, then the pinch off it is happening at the drain end, and then the expression of the current IDS of the device can be given by this formula, where VGS minus VT square it is having important role, and in this circuit this VG incidentally that is also same as VGS, and if the device it is in saturation region, then the current is having very weak dependency only through 1 plus lambda VDS part, which it is commonly known as channel length modulation factor. On the other hand, depending on the aspect ratio of the device W by L, of course, it is having good influence on the current, and the remaining part, particularly mu epsilon divided by T ox, this part it is, you may say that is a device constant. So, we may say that this is simply a constant K. Now, if you compare the common emitter amplifier circuit, which is similar to this circuit, common source amplifier, it is and the circuit, just for your reference, which it has been discussed previous class, I am also showing the circuit, and here we will try to see that once the circuit is given, how do we find the current here. Of course, the current equation is given here, and then subsequently how do you find the drain voltage or VDS, or in this circuit incidentally that is the output voltage. So, if you compare the common emitter configuration based on the bias condition at the base, we are suggesting to analyze the base loop to find the base current. Whereas, for this circuit, since the current is not flowing, of course, this model it will not work, and of course, the dependency of this IDS on VG or VGS, it is different from the BJT circuit. So, let us see what kind of equivalent circuit we should be using, and how this equation it is playing important role. In fact, this circuit, as I said, that we do not have any notion called beta of the transistor as we have seen for BJT. Instead, the VGS it is directly controlling the drain to source voltage, okay, and hence this equation it will be directly used. Whereas, for BJT, what we have done is that we have analyzed this circuit, then diode we have replaced by its simplified linear model by whatever VB in, and then its equivalent resistance and so and so to find the IB, and then we have used this beta. So, in this case, however, this part it is quite different, but of course, once you find the IDS, then finding the output voltage using the load line characteristic, that is similar, that is similar to the discussion we made for the circuit containing BJT. So, let us see what is the model we use for this circuit, and here again just for your reference, I am keeping the model corresponding to C amplifier here, and of course, this is our main circuit of our consideration. So, here as I said that this gate voltage it is forming or providing the VGS. So, this is directly coming to the gate, but then source, at the source we do have 0 voltage. So, we can say VG is nothing but VGS, and depending on this VGS, drain to source current is flowing. So, we can say that this device it can be modeled as voltage dependent current source. And so, we do have this IDS as function of VGS and also the VDS. So, this is the drain and this is the gate, this is the source, and whatever the voltage you do have across this output port, it is actually the VDS. So, the current flow here it is it depends on the VGS as well as VDS, and we know its expression. Just now we are talking about it is K divided by 2. K is the transconductance parameter coming from the device, multiplied by aspect ratio of the channel, multiplied by VGS minus VTH square, multiplied by 1 plus lambda into VDS, assuming that this condition is getting satisfied, namely the device it is in saturation. So, once we get this the current, definitely then we can see what may be the corresponding voltage here by considering this part and this part together, namely their characteristic we can combine to find the output voltage. As you have done for the BJT, similar kind of approach will be following. So, once the circuit is given to us, namely not only these voltages are given, we are also assuming that the corresponding device parameter, namely VTH, then K and then maybe the lambda, all are given. And here of course, in this module, simplified module, we have assumed that this lambda n is very, very small, namely you may say that approximately 0. So, this factor dependency of this current on VDS you can say practically 0. So, that is the assumption. Later on we will see that this approximation may be important only for DC, but once you go for AC signal, this may be very vital, we may have to consider that part. So, to find the operating point or to find the solution point for given condition, what are the steps we need to follow. So, let us see what are the steps we need to follow in the next slide. So, here we have written that okay, this is the equivalent circuit. So, this is the at this point we do have the VDS, and we also assume that this part it is very small. Okay. So, we do have only this current which is function of VGS alone, and so the first step it is we need to find the IDS, and then next one it is we can find the drop across this resistor while this current is flowing through this resistor. So, we can say that applying KCL here at the drain node, the same IDS current is flowing through this resistor, creating a drop across this resistor called say VR, which is having this side plus and this is minus. So, second step it is so it is basically IDS multiplied by R, it is giving us the drop across this resistance. Now, to find this VDS which is VDD minus this drop. So, that is the third step, and following this one we can find the circuit solution, namely the current and the corresponding voltage here. It is in fact this procedure or this whatever the steps we said, it is it can be viewed as more generalized approach, and graphically it will be very interesting to see, though actual circuit numerical solution we may be following this one, but many a times graphical representation may help you to understand whether the circuit will be providing meaningful performance, namely gain, or whether it is gain is sufficient, and under what condition the signal swing it will be good, or the signal will not be facing much distortion. So, to appreciate all these qualitative things, it is better to understand these steps in a graphical way also. So, in the next slide what we are going to discuss is the generalized method. In fact, this method we have discussed for the BJT circuit as well. So, let us see what are the steps we are following here. First step, it is of course, we need to find the IDS. So, that is we have to use this equation, and the next thing is that we need to find this voltage, we need to combine the characteristic of the upper element and the lower element. And as we said in the previous class, that let we call this is pull up element, and this one it is pull down element. So, we do have the pull down element, and if we combine say pull up and pull down characteristic, namely the voltage across this one and their current need to be consistent, and then we can find the solution point. So, pull down element characteristic, you may recall that similar to the BJT circuit, if we plot the IDS versus VDS for a given value of VGS, and as we said that lambda is very small. So, we can say this current is practically independent of this VDS. Assuming that the pinch off it is happening, that means we are not entering into this triode region, we are keeping the device in the saturation region. So, this portion it is saturation region, which is equivalent active region of operation of BJT. And then the pull up characteristic, that means the load line characteristic, it is of course, it is linear. So, if we draw the current through this resistor IR versus voltage drop across this resistance. So, the VR is the voltage drop across this resistance, and IR is the current flow through this resistance. And we know that if we plot this IR versus VR, this will be linear, and slope of this linear line it is 1 by R with a minus sign. And so, if we combine these two characteristic, then they will be giving us the solution. But since the x axis this is VR, and then here we do have VDS, they are not same. In fact, VR, if you see here, it is nothing but VDD. So, VDD minus VDS. So, since these two axes they are not consistent, even though finally we want this IR and IDS should be equal, but these two definitely we do not want equal, because rather it will be VR should be VDS. So, since we cannot directly combine these two characteristics, we need to change this characteristic. What we call it is, we rearrange this pull up characteristic and then we do the superposition. So, similar to the BJT circuit, what we do, first we flip this characteristic, namely we plot the IR versus minus VR characteristic, which is equal to VDS minus VDD. So, that gives us the characteristic of the resistor, it is going to the second quadrant. This slope, sorry, this will not be minus, this will be plus. Here the slope here it will be minus 1 by R. and then this axis, of course, it is having VDS with plus sign here, but still we do have the minus VDD part. So, to get rid of this one, what we do, we further rearrange this characteristic, namely we plot IR versus VDD minus VR. So, that is of course, it becomes equal to VDS. So, now of course, if you plot this characteristic it is getting shifted by VDD amount to the right, and so this is getting shifted here. So, the origin it is getting or rather this point of the characteristic curve touching the origin is getting shifted here to VDD, and the slope here of course, it remains minus 1 by r. So, considering this point and this slope, what we are getting here, it is VDD by r, that you yourself can find it. And now, this IR to satisfy KCL at this point, IR need to be equal to IDS, and this axis of course, it is VDS. So, now we can superimpose the two characteristic curve. So, this is the characteristic of the load line, and its slope it is minus 1 by r. So, wherever, and also this point is VDD, and wherever they are intersecting we call the solution point or the operating point. Now, so this procedure, as I said, it is very similar to the circuit containing BJT. If you see, so far we are talking about the circuit containing MOSFET, but this MOSFET is a special kind of MOSFET, or rather I should say it is N type. In case if you are finding a circuit containing PMOS transistor, then of course, the situation you need to adjust yourself, so that whatever the technique we are following here, that can be deployed. So, let us see an example having PMOS transistor. Okay, sorry, before we go to PMOS, I do have another case to discuss in comparison with BJT. What is this one? Is in case we are having input voltage, and then if it is having a resistance in series with that. So, let you call this is a R1, and then so this is same as whatever Vg, and whatever the analysis in this case, can we deploy, or how do we find in this the IDS and the VDS for this circuit. In fact, if you see here, since gate DC wise, through the gate the current is 0. So, we can say Ig is practically 0, even though we do have this resistance, a drop across this resistance is 0. So, we can say that whatever the voltage you are applying V in, it is directly coming to the gate. And if you see if you draw the equivalent circuit of the transistor, what you will be finding is that this resistor practically is not having any effect to the operating point. So, whatever the voltage you are applying here, even though we are applying through this resistor, say R1, so and let you call this is whatever I say V in, and since this current is 0. So, since Ig equals to 0, at least DC wise that is valid. So, the drop across this resistance is VR1 equals to 0. So, we can say that the voltage from the drain gate to source of this device, namely this VGS equals to same as this V in. So, as a result, whatever the IDS equation we are using, we can directly use that IDS equals to K divided by 2 W by L into V in, VGS equal to V in minus VTH square into whatever 1 plus lambda VDS and all these things. But anyway, we have considered this part is approximately 1. So, whatever the equation we do have here, it is essentially saying that this resistor is not having any role to play. However, if we are considering a signal you are applying here, the gate to source there will be capacitance. So, then for signal, of course, this resistor it will be having some role to play. So, that we will discuss later, but for the time being at least you can say that if you are having a resistor here, the DC condition wise it is not having any influence. In fact, this is a contrasting difference compared to the BJT circuit, where if you put a resistor and then if you put say V in to bias the base of the BJT, then we know that then the current flow through this circuit, it will be affected by this resistance. And so, this V in, even though we are applying V in here, the VB it will not be same as the V in, because there will be a finite drop across this resistance. So, this drop it will be non-zero. So, that is one important difference of the while you will be analyzing the circuit containing MOSFET and circuit containing BJT. And of course, later part it is this part it will be same for the two cases. And let us see, as I was giving a hint that so far we are discussing about the circuit containing in MOSFET, in type MOSFET or rather in channel MOSFET. In case if you are experiencing a circuit which is having P MOSFET, then what do you do? So, here we do have an example. In this case, this is the transistor of our consideration. Its source is connected to VDD. In fact, need not to call VDD, it is connected to source, but whatever the name you are giving, it does not matter as long as this is at high potential, at least compared to the gate, and creating a voltage drop here sufficiently high, so that the device it is on, that is good enough. Just for our consistency, we are naming this one VDD. So, you may not be sidetracked by that, but after that once we apply the voltage at the gate by the other source, then how do you find the corresponding current through this device? Now, if you replace this device by its corresponding model here, what we have it is so this is the source. In this case, this is the source, this is the gate and this is the drain, and we are expecting the current, it will be the actual current, it will be flowing from source to drain. So, we may call this is ISD, and we are expecting that VSG should be higher than threshold voltage of the transistor, magnitude of the threshold voltage, and also at the drain end, to have the pinch off happening, we need to satisfy VSD should be higher than VSG minus VTH. So, once we satisfy this condition, then the expression of this current is given by K by 2 W by L VSG minus VTH square multiplied by 1 plus lambda into VSD. Again, just for simplicity, we may consider this is approximately 0, but rest of the things it is very similar to whatever we have discussed. Only difference is that the source is connected to the supply VDD, gate is connected to at lower potential, and then of course, drain it is it is preferably in fact, it is lower than the source voltage, and preferably this drain voltage should be such that the pinch off it is happening, namely the channel is not appearing. In other words, the drain voltage should not be higher than gate voltage by a margin of magnitude of the threshold voltage. So, that is the condition we are writing here. And once it is done, once this condition is getting satisfied, then you can see what is the VSG, namely VDD minus VG. In this case, this is VDD minus VG. So, that is the VSG. So, we can say in this case, this is VDD minus VG. And so, that voltage we can plug in here, and then you can find this current, and this current is of course, it is flowing from source to drain. This current is also flowing through the resistor or load. So, we may call this is IR, which is equal to ISD, and that is producing a drop across this resistor called VR. And then this VR, incidentally, this is same as the output voltage. So, we may say that V out is same as VR equals to VDD minus VSD. Okay. So, of course, if you see the circuit, it will be relatively straightforward to follow, but then there will be a difference of whatever the generalized methodology we have discussed. So, let us see what kind of changes it will be there in that generalized methodology, or whatever we see graphical interpretation of the steps. So, let us try to see what kind of things we have to do here. First of all, again we may call this element and this element, they are trying to adjust themselves to converge to a point where this V out, it is consistent for the upper element as well as consistent for lower element, and this V out, of course, and this V D D minus V out, that is nothing but the VSD. So, since the device it is in saturation region, we may say that this current again it is primarily defined by VSG, and this part it is approximately 1. But then the main the change here it is, now we will be calling this is as pull up and this element as a pull down element. So, this is the pull down element. So, then while we will be rearranging the characteristic, which one do we rearrange? Interestingly, V out is this one. So, first thing is that let us draw the pull down characteristic first. So, we do have the pull down characteristic, namely IR versus V out, and incidentally that is the drain voltage, and we know that this is a linear element. So, we draw this one. Now, if you consider the pull up element on the other hand, so we know that pull up element is basically ISD versus VSD, and the VSD, what we said, it is VDD minus V out. So, this is equal to VDD minus V out. Now, again this V out and this V out, they are same, but then this axis and this axis they are not consistent, and of course, they are the characteristic, this is the pull up characteristic. If I ignore lambda part, it is supposed to be quote and unquote independent of the VDS or VSD, but then this axis we want this should be equal, but then the x axis parameter they are not same. So, what you have to do, we have to rearrange what we said, we need to rearrange this pull up characteristic. Incidentally, now this is nonlinear in nature. So, it is a bit tricky. So, first thing is that we need to flip it. So, let we flip and let the characteristic is going to the second quadrant, and the characteristic it becomes like this, it is going to the second quadrant. So, this is ISD versus minus VSD or whatever you say VDS, but then this is equal to V out minus VDD. So, again we do have V out, but still we do have minus VDD. So, to adjust that, what you have to do, we have to shift this characteristic towards the right by an amount of VDD. So, if you do that, then the characteristic it is getting shifted. So, now ISD versus VDD minus VSD. So, that is of course, this is equal to V out, and since we are adding this VDD part. So, this characteristic curve it is getting shifted to right by an amount of VDD. So, you may say that this is the VDD part, the VDD point. So, V out is equal to VDD here. So, so what are the things we have done is that we have flipped it, and then we have shifted right, and now these two axis, this axis and this axis, they are same. So, now I can overlay this characteristic on the pull down element, namely the characteristic it becomes like this. So, we do have the VDD here, and wherever they are intersecting, we call this is the operating point. So, that is I think the method it is remaining same, only thing is that you need to be comfortable to rearrange this pull up characteristic, even though it is not linear, and incidentally the pull down characteristic it is linear. In general, so you should be comfortable even if say both the elements pull up and pull down elements, they are non-linear in nature. So, let me take a short break, and then we will come back to the subsequent point.